So in this section, I'm going to talk right at the smallest level inside of the computer, at individual bits and bytes. So a bit in the computer is the smallest amount of storage that you can have, like an atom. So a bit just stores a 0 or a 1. Those are the only two states it can do. So you may have heard the expression, oh, well, in computers, it's all zeros and ones. That's referring to bits. Everything in the computer is built up out of these larger and larger collections of these simple bits, which are just 0 and 1. So in the hardware, anything that can it's capable of taking on two different states, and when it takes on one state, it can stay in it. That's how you can represent a bit in hardware. And there's a bunch of different ways of doing it. I've actually, just as a prop, I've built this bit here. So this is a bit made out of a tennis racket with some plastic in it. And the way this works is that it has two different states. So I'm going to just call this state the 0 state. And then I could push it into the other state. There you go. The plastic snaps and it stays. We'll call that the 1 state. So I could switch it back to 0. There's 0. Turn around. There's 1. So it's a trivial example, but at a hardware level, this shows, well, yeah, if you have two different states and they're stable, when you put it in a state, it stays, that's enough to represent a bit in the computer. And we see different forms of it. So with a transistor, the two different states are done by having little tiny groups of electrons. On the hard drive platter, the two different states are done by having either a little area set to either north magnetism or south magnetism. And then later it can come back and look. And you just designate, oh, well, we'll say if it's north, that's a 1. If it's south, it's a 0 or whatever. So the bit, just by itself, it's too small to be good for anything. It's just 0 and 1. So really what we're going to do is to group 8 bits to make a byte. And the byte is just this very common unit of measurement. So if an example byte is written out, I sort of think of it like this. Like, well, you're going to have 8 digits, but the digits are binary. So each one is just a 0 or 1. And so any byte we could think of is just going to be this pattern of 8 zeros and 1s. As I mentioned before, a byte in the real world, you can think of it as storing kind of one typed letter. So it's pretty small. It holds very little, but we can build up other measures out of it. So the question I want to look at is exactly how much can 1 byte hold? And I want to work out the math for that. Now, I'm not going to hold everyone responsible for the details of this, but I want to go through the derivation just so you can see it. So the question I'm going to explore is, if I have a number of bits, how many distinct patterns can I make with those bits? And first we'll just consider either 1 bit, 2 bits, or 3 bits. So I've put these in a little table. So if I have 1 bit, I'm going to say, this one you can do in your head. There's just 2 patterns. Either it's a 0 or it's a 1. There's not some third pattern. That's it. 2 is all we can do. So suppose we've got 2 bits. So I'm going to imagine putting the 2 bits next to each other. So there's like a left bit and a right bit, and then we can work out the patterns for that. Well, let's see. There's the pattern where both bits are 0. Then there's the pattern where the left bit is 0 and the right bit is 1. And then going the other way, we could have the left bit be 1 and the right bit be 0. And then finally, there's the case where both bits are 1. So with 2 bits, I can get 4 patterns. Now for 3 bits, it gets a little more complicated. So I'm gonna sort of break the problem down and walk through how many patterns that's going to make. So for 3 bits, the trick is going to be, so here's the 3-bit case down here. Just consider, so I'm imagining I have 3 bits next to each other. Just consider the leftmost bit. Let's just isolate on the leftmost bit. And there's only 2 possibilities. Either the leftmost bit is 0 or the leftmost bit is 1. Those are the only two possibilities. So let's just consider the case. Just suppose it's 0. Just suppose it's 0. So that's going to give me this top row. Well, if I just lock the leftmost bit at 0, then I've got these other 2 bits to the right of it. But actually, we've already worked out how many patterns are possible with 2 bits. That's my row up here. There's 4. There's just 4 patterns. And so if I lock the leftmost bit at 0, then I get 4 patterns because I have 0 and then each one of the 4 patterns for 2 bits. So in this highlighted row, that gives me 4. So that was the case where the leftmost bit is 0. Well, what's the other case? The other case is that the leftmost bit is 1. And if I lock the leftmost bit at 1, I just get those 4 patterns again. Like I still have 2 bits to the right, and so I get, in a sense, another copy of the 4 patterns that can be made with 2 bits. So for 3 bits, it works out actually that there are 8 patterns. And I'm thinking of them as kind of like, well, there's the 4 with the leftmost bit as 0, and then there's 4 again with the leftmost bit as 1. So if you, in general, you can see it here even in my little table, for each row, on the next row, you're basically adding a bit to the left. And so what that's going to do is just double the number of patterns that you have in the row above. And so I've run through the math here. So with 1 bit, we saw that there were 2 patterns, just 0 or 1. So then when I go to 2 bits, I get 4 patterns, and 3 bits, I get 8 patterns. But if you just look at the numbers here, you can see it's doubling. It goes 2, 4, 8, 16. So each time I add 1 bit, which I'm thinking of as sort of going on to the left, it doubles the number of patterns I can make. So if we just follow this through, it goes 32, 64, 128. And with 8 bits, there are 256 different patterns possible. And of course, 8 bits, that's the size of a byte. So it works out. 1 byte can store 256 different patterns. Mathematically, it turns out to be exponential. So with n bits, I can make 2 to the nth different patterns, 2 to the nth power. So the case I want to focus on is 1 byte. And here's what you need to know. So 1 byte is a group of 8 bits. And I've sort of gone through the derivation that with 8 bits, 256 different patterns are possible. So I think the natural question is, well, pattern, and what's that good for? Really what I want to do is think about how can I use those patterns to represent numbers. So the way I'm going to think about numbers is each number is going to get one of the 256 different patterns. And I'm not going to get into details of how they're assigned, but each number needs its own, and it can't share a pattern with some other number. So the way I'm going to think about it is just, well, look, let's give some pattern to number 0. So we've got 256 patterns. We'll give one of them to 0, and then we'll give another pattern to 1, and another pattern to 2, and another pattern to 3, and so on. And we'll just sort of keep going until we run out of patterns. So the way it's going to work is we'll get up to 254, and then the last pattern, we have one left, we'll use for the number 255. So 255 will be the maximum representable number in 1 byte. I think a reasonable question would be like, oh wait, 255, why isn't it 256? We have 256 different patterns. And the reason it's not 256 is that we used one pattern for number 0. So we use that one up, and then if you just count up the number of numbers I have here, 255 is going to require the last pattern number 256. So turns out, if you think of what can be stored in 1 byte as a number, the common representation is that 1 byte will store numbers between 0 up to 255. So 255 is the max. So this actually came up earlier when we were looking at code like pixel.setRed. And what number did it take? Pixel.setRed takes a number in the range 0 to 255. Why? Why? And the reason is that the red value for a pixel in the computer is stored in 1 byte. And that byte can store numbers in the range 0 to 255. That's it. It cannot store 300 or minus 12 or whatever. So that's why in this scheme, setRed takes a number 0 to 255. It actually reflects that the red value, and this is also true for the green and the blue values, each one of those is stored by 1 8-bit byte. And so that's why the range is exactly 0 to 255. So the mystery of the 255, now you know.